Talbot, and I will be presenting galactic cosmic rays. Alright, so for an outline, I'm going to start off talking with some background on cosmic rays. I'm going to move into the formation of cosmic rays. I'm going to talk about the acceleration mechanisms behind how they're powered, and how we can measure them, and then their overall effect on Earth. So, cosmic radiation was discovered over 100 years ago. It was discovered that air was being ionized very rapidly at about 10 to 20 ions per second per cubic centimeter. And basically, ionization is the process by which atoms gain or lose or acquire a charge by gaining or losing electrons. So if they gain electrons, they get a negative charge. If they lose electrons, they'll have a positive charge. Originally, scientists were not aware what was causing this ionization. We knew of the properties of alpha and beta waves, and they knew that they could not be the cause of the ionization. So it was hypothesized that gamma rays were producing this ionization. Eventually, the gamma rays were re-clarified as galactic cosmic rays, or GCRs, which were declared as the driving force of this ionization. So, cosmic rays consist of subatomic particles, not photons. That's why they re-clarified them from gamma rays into galactic cosmic rays, because they can't produce light like gamma rays can. They're called cosmic rays for the radiation that they produce. That's why they're called rays. When they're created, the nuclei, their electrons, are stripped by how fast that they're powered, and they consist mostly of hydrogen, 90%, with 9% helium, and then 1% of every other element on the periodic table. This picture shows the cosmic rays hitting Earth's atmosphere and splitting, which I will be talking about in later slides. So they can travel very long distances. In their lifespan, around 10 million years, they can travel across the galaxy multiple times. They can reach speeds very close to the speed of light, but will never actually get there because they are made of matter, not photons. They most have a possible electrical charge because they're made mostly of hydrogen, and they can have energy several times higher than 10 to the 16 electron volts. And an electron volt is the amount of energy gained or lost by a charge of a single electron as it's moved across a potential difference of 1 volt. It's also equal to 1.6 times 10 to the negative 19 joules, in case any of you guys are curious. There are specialized cosmic rays called ultra-high energy cosmic rays, which have energies up to 10 to the 21 electron volts. These are more rare than regular GCRs because as they travel through space, they're going to lose their speed faster as they collide with more molecules in space. They're formed in the early universe by gamma ray bursts, gamma ray bursts can occur in the Milky Way galaxy, which is where the UHDCRs we experience on Earth when air showers come from. For the formation of them, they originate from areas of space where very large amounts of heavy elements exist. Scientists have kind of put this information together because when the cosmic rays that they have studied have a very high percentage of heavy elements in their composition, larger than the percentage of heavy elements in matter on Earth. So they can deduce from that that they have come from other areas in space that have higher concentrations of heavy elements. They must also originate in an area with a large magnetic field, because the magnetic field is going to help accelerate the particles when they're created. And it is hypothesized that GCRs present in our own galaxy have had to be created near or relatively close to Earth, because our Earth's magnetic field traps the GCR particles, and if they were produced too far away from that magnetic field, they would have escaped into other parts of space. So the speed of cosmic rays can be produced from quite a few things, including supernova remnants, the sun, the galaxy, the radio galaxy, and the metagalaxy. Supernova remnants will accelerate the GCR with their magnetic field. As I was talking about before, the particles are going to bounce back and forth in the magnetic field, and when they have gained enough energy, they're going to escape from the magnetic field and travel out into space. The larger the strength of the supernova remnant, the higher the acceleration of the GCR particles will be. So here I have a table of the three main stages of acceleration. There is the injection phase, the main acceleration phase, and the modulation phase. The injection phase is the starting accelerator of the GCR, and it varies depending on the source, as you can see here. So for a GCR that was accelerated by the sun, the starting force behind the acceleration would be a solar flare. Then it goes through the main acceleration phase, which, as you can see, some of them are still unknown. Research hasn't clarified exactly what these main acceleration stages consist of for the bottom three, galaxy, radio galaxy, and metagalaxy. And then the modulation phase is an adjustment phase, where the acceleration of the GCR can vary in intensity. As you can see here, they're all different for the different mechanisms of acceleration. So how can we measure cosmic rays? There's actually a lot of methods we have to measure them, but none of them are very simple, because Earth's magnetic field is going to curve the paths that the GCRs take when they're arriving at Earth. So from this picture, the dotted line is the predicted trajectory of the GCR, but the actual curved path is the path that they'll take when they interact with our magnetic field. That makes it harder to measure where they came from directly. Also, GCRs, when they impact Earth, they're going to impact it from every direction, like a blanket out in space, which makes it even harder to determine their origin. But if you take a look at the composition of the elements in the specific ray that hits Earth, they're trying to pinpoint from that where in space they originated from. This is one method for measuring cosmic rays that we have here. It's called a scintillator. And basically, the cosmic ray particles are going to hit the scintillator, and they're going to excite the atoms of the detector in the scintillator. Those atoms will lose their energy by producing light, and then another detector called a photomultiplier is going to take that light and transform it into a larger electrical signal that we can measure. So the higher the signal, the more particles are hitting the scintillator. We also have, on two of our Voyager spacecrafts, we have galactic cosmic ray measuring devices that pick up on the hydrogen and helium that are present in the rays. And because they're made mostly of hydrogen and helium, they can pick up on the rays coming towards Earth. It's also possible for us to deduce some of the secondary rays, which I will talk about later, such as aluminum-26, chlorine-36, and others, they will begin to decay as soon as they're formed. So when they reach Earth, if they've decayed more, the rays are then considered older than if they've decayed less when they reach Earth. We also use particle accelerators on our surface to measure galactic cosmic rays, and they're going to measure the collisions between primary and secondary cosmic rays. Larger number of secondary cosmic rays indicate that the GCRs have traveled farther because the secondary rays are formed when the primary rays collide with other nuclei and split into smaller pieces. They also have used a very strong magnetic field to curve the path of the GCR, which the curve can then be measured and related to velocity. Because I didn't study all the integrals involved with measuring them, I'm not exactly sure how they relate them, but I know that they've used that method. They can use that method. And a Geiger-Moller counter is used similar to the scintillator. It gives a pulse after a charged particle has passed through it. They use it to measure radiation on Earth now. It's not super effective for cosmic radiation unless you're on the surface, because it can only measure the smaller amounts of it. Most of the GCRs that we experience that hit Earth's atmosphere are deflected by our magnetic field. Here is a graph of intensity of GCRs with altitude. So as you can see, as the altitude increases, the strength or the intensity of the GCR also increases. This drop right here at the end is because they measured secondary rays, which, as I said before, are formed when the primary ones collide with atmospheric nuclei. So at the very high altitudes, there's going to be a lot of radiation, of cosmic radiation, but it's going to be in the form of primary rays because they haven't had the chance to collide with atmospheric nuclei. This graph, or this data, proves that the radiation is coming from space because as it increases, as altitude increases, there's more radiation. And like I said before, there's two types of particles, primary and secondary. The primary ones, again, arrive directly from space, and the secondary ones are primary and have collided with atmospheric nuclei and split into ions and other smaller pieces. So cosmic rays that do hit Earth can contribute to the formation of clouds because they serve as condensation nuclei. When clouds are formed, the water vapor wants to have something non-gas to change from vapor to gas, change from gas to vapor to form the clouds. So that's what some of these particles can serve as. Some research also shows that GCRs can create new ozone, which I found was very interesting. It says that the reaction between OH and CH4 or methane could produce OH, but other research has provided a contradictory argument to this, saying that GCRs can help increase CL, at least in our atmosphere. They're not the they don't produce it, but they can help CL be reduced from something called human source chlorofluorocarbons. So that's where the chlorine comes from, but their reactions with those compounds release chlorine into the atmosphere. Increasing chlorine is linked to ozone depletion. So basically, in summary, cosmic rays are subatomic particles with electrons that have their nuclei nuclei that have their electrons stripped. They produce radiation and ionize air very rapidly. They're made up of mostly hydrogen, some helium, and then a small amount of other elements. How are they powered? They can be accelerated from the sun, from supernova remnants, from the galaxy. They're mostly powered through a strong magnetic field. And we can measure them using various methods, but we cannot directly measure them because they all can come from every direction. And they don't have a very large effect on Earth. So most of our galactic cosmic rays are, again, diffused by pushed away by our magnetic field. But they pose a problem for astronauts out in space. So we're still working on new research to help deflect some of the cosmic radiation up there. Basically, in summary, there's a lot of research that still needs to be done on this topic. Like the chart I showed you, they're still missing some information on some of like acceleration, or they don't even know the origin of a lot of cosmic rays. So it's not a new science, but they're still working on a lot of the data.